Welcome back, Chem 51, to your Week 4 lecture. This lecture covers sections 3.1 through 3.9 in McMurray and activity 36A in the lab manual. So please read both before you watch the lecture. And you do not have to complete anything from activity 36A. You'll find what looks like a worksheet. You're going to do that in class. Um, and then you'll have something else to turn in, like it's for your own notes. So please leave it blank. So as we learned in chapter 2, elements can gain or lose one or more electrons to become charged. And form what we call ions. So metals, located on the left of the periodic table, those tend to lose electrons. And those will become positively charged. And so nonmetals on the right of the periodic table, those tend to gain electrons. Okay, so let's draw a picture of lithium. So we have 3 protons and 2 shells. And so it has its 2 electrons in its 1s orbital and then 1 electron in its 2s orbital. So what's going to happen here is it's going to lose the outermost electron and downgrade to its 1s shell, its 1s orbital. So this would be lithium plus, since we have 3 positively charged protons in the nucleus and then 2 negatively charged electrons in that 1s orbital. So let's just draw the brief electron configuration for this. You'll see from here, just with 1 valence electron. And now that 2s is blank. So you have a full shell. Okay, so let's look at some nonmetals. So let's look at fluorine. Let's just look at neutral fluorine. So we have +9 in our nucleus. Two electrons in the n=1 shell, and then 7 electrons in its n=2 shell. And I'm just worried about the shell. I'm not worried about the orbitals. Okay. And so what this nonmetal is going to do is it's going to gain an electron. And then it's going to have a full shell. And it's negatively charged because it has 10 total electrons. So here we've got 1s, 2s, and a 2p. Okay, remembering not to pair them off until we have to. Okay, so we have here in our valence shell 7 electrons. But here we've gained 1. So our valence shell contains 8. Sorry, that was a funky looking electron. So we just alluded to something. Lithium up here, we said it had a full shell having its n equals 1 shell filled with 2. So the n equals 1 shell is so small, that's as many as it can fit. It's full. But when we get into the p orbitals, then we can fit 8. That's the maximum number that we can fit. And that is called a full octet. And so I want you to think back and consider the electron dot symbols. And those were on table 2.5 on page 65 of McMurray. And they show how many valence electrons an element has. Okay, so the noble gases, that's group 8A, and those will have 8 valence electrons. And so that's our full octet. So as you can hopefully see here, what these elements are trying to do when they ionize is get a full octet by either losing or gaining an electron. And when they lose, they downgrade to their previous shell. The previous core shell becomes the valence shell. So ionization is all about how many electrons an element needs to have its full octet. So metals, if you look at table 2.5 still, those have so few valence electrons that it is much easier for them to lose them and downgrade to the next shell down. Okay, nonmetals, though, have so many electrons, they're closer to having a full octet. They're at least over halfway, so they tend to gain electrons to complete it. So, for example, K with its 1 electron plus Br from group 7A with its 7 electrons, that's going to form K plus, positively charged, it lost its electron, plus Br minus, and it has 8 electrons. Okay, so potassium has downgraded, and bromine has filled its outer shell. So it just says the group number, indicates the number of valence electrons it has. It also indicates the charge of the element when it ionizes. So I'd like you to look at figure 3.1 on page 76 of McMurray. And so you'll see that main group elements, when they ionize, have fixed charges. They're always the same. They only form one type of ion. So those would be the main groups, metals from groups 1A and 2A. So for example, sodium has its one valence electron, so it forms a singly charged ion. And so everything in that column in group 1A forms a +1 charge. And so calcium in 2A has its two valence electrons, so it's going to form calcium 2+. Okay, all nonmetals have fixed charges, and those are groups 5A through 7A. So in group 5A, we have nitrogen, and that has 5 valence electrons. So it's going to gain 3 electrons and form N3-. We're not always going to draw these as electron dot structures. At some point, we're just going to draw them like this, just indicating the charges. So 5A, 5 valence electrons, it needs to gain 3 for a full octet. So 6A would be something like oxygen. It's got 6 valence electrons, so it needs 2. And it forms O2-. Okay, and we'll draw it over here, group 7A. Fluorine, with its 7 valence electrons, gains 1 electron to form F- with its full octet. Okay, so there are some patterns on ion formation on the periodic table. And so ionization energy is how much energy is required to yank off an electron. You have to add energy to remove an electron, forming a positive ion. Okay, so the other property that's important is electron affinity. Oop. And that's how much energy is released to gain an electron. So, so it's like you're getting paid to gain the electron. So those would form a negative ion. And so both properties tend to increase as we go from left to right on the periodic table. Okay. In other words, elements on the left side of the table tend to lose electrons, and elements on the right side of the table tend to gain electrons. And so this is due to the increasing number of protons. If you look at one period, one row at a time, you have an increasing number of protons from left to right. And it looks like I forgot to make that blank. So it's an increasing number of proton for the same number of shells. And what this does is it increases the effective nuclear charge. And another property that effective nuclear charge affects is the atomic radius. So let's look at an example. You'll see what I mean. Okay, so we have lithium. That's 3 protons, and so 3 positive charges. And that is pulling so hard, only so hard on these electrons. So that's lithium. If you have fluorine, we've got +9 in the nucleus. We've still got the same number of shells. So since you have that +9, those shells are going to end up being a little bit closer. They're being pulled in more by that nucleus. I know this is barely smaller in the drawing, but it's supposed to be significantly smaller. So what we have here is increased ionization energy. I'll just put E for energy, um, because those outer electrons are being held on so tightly by this +9 nucleus that it's harder to remove them. So it increases electron affinity. It's more likely to pull in an extra electron. Oh, and I actually accidentally added too many electrons. There we go. Should be 7 electrons. And another thing is that it decreases atomic radius. Okay. That goes a little bit farther than the book goes on this topic. So let's talk about naming. That's the main thing for the activity that we're doing this week. So let's start with naming monatomic ions. So these are single atom ions. And so they're single atom charged elements, and they have naming rules based on their type of charge. So positively charged ions, those are called cations, not cations, cations. And they just have their element names followed by the word ion. Put that in quotation marks. Okay, so metals from groups 1A and 2A have fixed charges. So those charges do not need to be specified in the name. Okay, you don't have to say anything about what charge it is. We just assume that everybody knows what it is because they can see where it is on the periodic table. But there's also the transition metals. Those are in groups 1b through 10b. And so those have variable charges, so we do have to specify them in the name. So we're specifying those by Roman numerals. Okay, so sodium. Sodium forms a +1 ion. We know that. It's in group 1a. So we're just going to call it a sodium ion. Calcium 2 plus. Same thing. We know it's calcium 2 plus because of its location. So I'm just going to say calcium ion. But this iron, it could go 2 plus or 3 plus. It's a transition metal. So I'm going to specify. So this one is iron in parentheses 2, Roman numeral 2, ion. And then so you could probably guess what this one is going to be. Iron 3, ion. Okay. So what about negatively charged ions? So negatively charged ions, those are called anions. And they have their element root name, um, but they're followed by the suffix "ide" and then followed by the word ion. So Cl minus, I would just say chloride ion. And I'm not specifying the charge because anions are always fixed charge. So we know based on the periodic table what charge it's going to be. So O2 minus, oxide ion, N3 minus, nitride ion. Okay, if we have monatomic ions, we have polyatomic ions. So these are molecules, which we will go over in chapter 4. And looks like I forgot another blank here. So a molecule is a whole bunch of nonmetals um, bonded together. And a polyatomic ion is many nonmetals bonded together with an overall charge. So it's good for us to just look at a polyatomic ion as if it's a single unit. So you could even replace it with a variable if that helps you think about it that way. So I'd like you to see table 3.3 on page 83 of McMurray. And those are the polyatomic ions that you must be familiar with. And I'm so sorry to say that the best approach is to memorize them. Make some flashcards and memorize them. There are some patterns that I'll point out right now, but it's still mainly memorization. So SO4 with an overall charge of 2 minus is called a sulfate ion. Okay, but SO3 is a sulfite ion. So SO4 versus SO3, it would seem for a second like sulfate would mean 4 oxygens and sulfite would mean 3 oxygens. You might think that at first, but this NO3 is nitrate, the nitrate ion, and NO2 is the nitrite ion. So if you looked at these two in isolation, you might say nitrate means 3 oxygens and nitrite means 2 oxygens with those eights and ites. But if you look at them together, it's the relative number of oxygens within that family. So in general, 8 ions have one more oxygen than 8 ions. And so that's regardless of the actual number of oxygen atoms, it's just the relative number of oxygen atoms to each other. So let's talk for a moment about what an ionic bond is. So an ionic bond is an exchange of electrons. Um, and it's an exchange of electrons between the correct number of ions for the overall charge to equal 0. Okay, so an element that tends to lose electrons will join one that tends to gain electrons. And that forms an ionic bond. So if you have sodium with that one dot plus chloride, they will ionize. And then form a bond where the charges will cancel each other out. So now these final pages are going to be what's most applicable to the activity that we're going to do. And that's all about determining the formula and determining the name of ionic compounds. So a chemical formula contains the symbols for each element, followed by the number of atoms in subscript. In subscript. And so we determine the number of atoms of each atom by its charge. And what we're doing is we're finding the least common multiple for the charges of each ion. Okay, so when ions have equal and opposite charges, so they easily pair up on a one-to-one basis. Just like that sodium chloride that we looked at, one-to-one basis, plus minus. Okay, but when the charges are unequal, we're going to need multiple of each ion for the overall charge to equal 0. So let's look at some examples, or one example, and then the next concept. So I'm taking 2 sodium ions and 1 oxide ion, and that will give me Na2O. I need, so my least common multiple is 2. Least common multiple between plus 1 and minus 2. So between 1 and 2 is 2. And so I need 2 sodiums. To balance the charge. Okay. On the next example, we have three magnesium 2 plus ions and two nitrogen, or sorry, nitride 3 minus ions. And so my least common multiple between 2 and 3 is 6. So I need 2 Mg, sorry, that was sloppy, Mg2 plus um, to make plus 6. And I need, oh no, excuse me, this is supposed to say 3. I need 3 Mg2 plus. To balance out, I need 2 and 3 minus, 2 nitride for negative 6. And then the charges are balanced. So that is how we solve the puzzle of how many atoms of what ion, or it's kind of a weird way to say it, but how many of each ion we need. So, and our next topic is, I should say our subtopic, is formulas of ionic compounds with variable charges. So when you have a compound containing transition metals, so those will have varying numbers of anions such that the overall charge still equals 0. So for example, I have iron 2 and 2 chloride ions. So I have this 2 out front here to make sure I'm saying that there are 2 individual chloride ions with a single charge. I don't have 2 chlorine atoms bonded together with a 2 minus charge. Not at all. It's 2 individual chloride ions. And those will form FeCl2. So I need 2 Cl minus. And same thing here, if I have Fe3 plus, I need to have 3 Cl minuses. And so finally, we have formulas for ionic compounds with polyatomic ions. So if we have a single polyatomic ion, so for example, if they go together, not necessarily on a one-to-one basis, but you only need one polyatomic, then it's just written as is. There's no special modification. But if you have multiple polyatomic ions, then you've got to put the formula in parentheses with the number of ions outside. So we'll look at an example on the next page. So this first example, I have sodium and nitrate, and those have equal and opposite charges. They just go together on a one-to-one basis. So we have a single polyatomic ion, nothing special. But here, with calcium nitrate, I have 2 nitrate ions. And again, since I'm viewing that NO3 formula as its own single unit, I'm putting that 2 in front of it to indicate that there are 2 of that single unit. I'm not distributing that 2 anywhere. So if I have 2 polyatomics, I put it in parentheses. And that too applies to everything inside the parentheses. We're just indicating that the NO3 is its own independent thing. So in our final section, section 3.9, we're going to talk about naming conventions for ionic compounds. So if given the formula of an ionic compound, the naming conventions start out the same, and then it diverges based upon what type of charge you have, a fixed charge or a variable charge. So you're always going to name the cation first and the anion second. Okay, so monatomic anions are given the suffix "ide" still, and polyatomics polyatomic anions are not given a suffix. They are just written as is, as if they were single. Okay, so the number of each atom in any of these formulas is not specified, or in any of these names. I'm saying these names without numbers indicating the number of atoms. But the number of atoms is actually determined by the charge. So ionic compounds with fixed charge cations, those need no specification of charge. So Na2S, I'm just going to call that sodium sulfide. I am not specifying that there are two sodium atoms in there, or I should say two sodium ions. I'm just expecting you to know that there are two sodium ions because you know how to balance the charges, which means you'll have to have a periodic table in front of you. So charges are known here. Same with calcium chloride. Okay, I know that calcium is 2 plus, and I know that chloride is 1 minus, so I know there has to be two chlorides in there. So I don't need to state that in the name. So the second option, of course, is ionic compounds with variable charge cations. And these are the transition metals. These problem children, of course. So just like when we name the ions themselves, within an ionic compound, we are going to use the Roman numerals. So for example, if I have FeCl3, I'm going to specify the charge of the Fe, not the number of Cl's. So this is going to be called iron 3 chloride. I'm specifying the charge of the iron, not the number of chlorides. I just know there's 3 chlorides because I know the charge of chloride. So the trick to naming is we're trying to describe everything we possibly can about an ionic compound while saying as few English words as possible. And that's why we have such a specific system for it. So this concludes week 4 lecture. Thank you for your attention, and I encourage you to look at the reading again and read it in more detail the second time around. And I look forward to seeing you in class. Thank you.